In this video, I want to solve some more problems, problem number 6 to 10 of problem set 4.2 of the book D.M. Burton, 6th and 7th edition. I've already solved the question number 1 to 5 in my last video, link added in description. Now let's start looking at the problem number 6. It says for n greater than or equal to 1, use congruence theory to establish each of the following divisibility results. Although we can prove these results by induction also, but here they're asking specifically to use the congruence theory. And then we'll follow the question number 7, 8, 9 and 10. So let's first look at the question number 6a part. So in question number 6, for n greater than 1, I want to use congruence theory. The first part is 7 divide 5 to the power 2n plus 3 into 2 to the power 5n minus 2. So for proving this, let's start from looking the 5 and 2, and here I want to take with respect to mod 7, or in the congress I want to show 5 to the power 2n plus 3 into 2 to the power 5n minus 2. This is congruent to 0 mod 7. If I can show that this left hand side is congruent to 0 mod 7, then this result is true. And so for this I require some powers of 5. So we notice that 5 square, which is congruent to 25. 25, this is congruent to 4 mod 7. Because 25 minus 4 is 21 and 21 is divisible by 7. Now I can raise any power. So this is a simple property of the congruences, that if A is congruent to B mod n, then we can raise any k power, where k is any positive integer, mod n. So I'm going to use something like this, 5 square raised to power n, which is congruent to 4 to the power n mod 7. And let's keep this as equation number 1. We also notice, because we require some 2's exponent, 2 to the power exponent, so we have 2 to the power 5, which is congruent to 32, and 32 is congruent to 4 mod 7. So since 7 4s are 28, so this is congruent to this. Again, I'm going to repeat the process. 2 to the power 5 raised to power n, this is congruent to 4 to the power n mod 7. And then we notice that 2 to the power 5n into multiplied by 4 inverse on both sides. So we can again use 4 inverse on both sides. Multiply if A, so if A is congruent to B, then we can multiply AC is congruent to BC mod n. So this is another property of the congruences. And then we can have 2 to the power 5n minus 2, because this 4 is 2 square, and so I can take it as minus 2. This is congruent to 4 to the power n minus 1 mod 7. So here we get 3 into 2 to the power 5n minus 2, congruent to 3 into 4 to the power n minus 1. I multiply both sides by thrice because I require this in my original problem that I want to prove with respect to mod 7. And let's call this as equation number 2. Now add 1 and 2. So when I add 1 plus 2, what we get? We get here 5 to the power 2n. So you can see that here we got 5 to the power 2n plus 3 into 2 to the power 5n minus 2. This is congruent to 4 to the power n, which is here 4 to the power n, plus this equation number 2, 3 into 4 to the power n minus 1. Both are with respect to mod 7, so we can write with respect to mod 7. Take out 4 to the power n minus 1. Inside we will have 4 plus 3, and 4 plus 3 is congruent to 4 plus 3 is 7. So this is 4 to the power n minus 1 into 7 mod 7. And once this becomes as a multiple of 7, and we have already noticed that n is greater than or equal to 1, which means even if n is equal to 1, this term 4 to the power 0 will become 1 into 7. So this is congruent to 0 mod 7. So this is a multiple of 7, and hence this is congruent to 0. That proves our first part, that 5 to the power 2n plus 3 into 2 to the power 5n minus 2, this is congruent to 0 mod 7. That proves our first result. Now in the similar line, I am going to prove the second part. Here I want to show 13 divides 3 to the power n plus 2 plus 4 times 2n plus 1. To show this, let's again observe 3 is congruent to 16 mod 13. And we also see 3 is congruent to 4 square mod 13. So now just raise the power 3 to the power n. This is congruent to 4 to the power 2 times n mod 13. and we can have 3 to the power n plus 2. That means 3 square I have multiplied on both sides. So this becomes 4 to the power 2n into 3 square. Or I can write it as 9 into 4 to the power 2n mod 13. And let's keep this as equation number 1. That solves my first part. Now I need 4 to the power 2n plus 1. So what we can do is either we can reduce this as I did in my first question, or we can add on both sides by the same quantity. So here 3 to the power n plus 2 plus 4 times 2n plus 1, added this on both sides, 9 into 4 to the power 2n, and then I've added 4 to n plus 1. So this integer I've added on both sides, and then we take with respect to mod 13. Now we can see that this is 3 to the power n plus 2 plus 4 times 2n plus 1 as it is, and I take common 4 to the power 2n. Inside will have 9 plus 4. Now 9 plus 4 is 13, so 4 to the power 2n, and here we have 13, and this is with respect to mod 13. So this appear as a multiple of 13, and hence this is congruent to 0 mod 13. And this is what we wish to prove, that 13 divide 3 to the power n plus 2 plus 4n plus 1. So that proves our second part as well. Now in C part and D part, we follow the similar technique. We first start by reducing the exponent 2 to the power 5. We get this first equation, and then we add on both sides 5 to the power n plus 2, and we achieve this, that this is congruent to 0 mod 27. Similarly here in the D part, we reduce our one of the exponent, and then we add the remaining exponent on both sides, which is required in the problem. So either you can start by looking the exponent 6 and add this on this side, or we may start with this one and add this on both sides, and then we see that this is congruent to 0 mod 43. Now in question number 7, we want to prove for n greater than or equal to 1, this congruence hold true, and we will prove this by induction. So we'll proceed here by induction. So we'll take n is equal to 1. Whenever n is equal to 1, the left hand side is minus 13, 1 plus 1. So that is minus 13 square. And on the right hand side, we got minus 13 to the power 1 plus minus 13, 1 minus 1 mod 181. So this is the right hand side. And so we notice minus 13 square, this is congruent to minus 13 to the power 1 plus 1. Anything raised to power 0 is 1 mod 181. This is congruent to minus 13 plus 1, and here we got minus 13 square, which is 169, and 169, this is congruent to minus 12 mod 181, which is true. We can see that when we take minus 12 on this side, we got 181, and hence this result is true. So we assume the result for n is equal to k, and for n is equal to k, we'll have minus 13 to the power k plus 1. This is congruent to minus 13 to the power k plus minus 13 to the power k minus 1 mod 181. This hold. So this we are assuming, and we will prove for n for k plus 1. So for k plus 1, we will have minus 13 to the power k plus 2, because when I put k, n is equal to k plus 1, we'll have k plus 2. This is congruent to minus 13 to the power k plus 1 into minus 13. Now use the previous induction step, this step, to put it here. This is congruent to, or we can say star, and here I'm going to use star. So this I'm replacing with this side. So this will become minus 13 to the power k plus minus 13 to the power k minus 1. And then this is multiplied by minus 13, which is this integer. Now this is further congruent to, when minus 13 is multiplied to this one, we get minus 13 to the power k plus 1. And the second term will become minus 13 to the power k mod 181. And this is what we are supposed to prove. We see that here, if it is n plus 1, we got n, and then we got n minus 1. So for k plus 2, we do require here k plus 1 and k, and hence the result is true by induction, hence proved. Now in 8th A problem, we want to show that if a is odd, then a square is congruent to 1 mod a. That means square of an integer, whenever a is odd, this is congruent to 1 mod a. We can take the possible values for a. Let's say a is of the type 4k plus 1 or 4k plus 3. These are the possibility for a to be odd. If I'm just considering a to be in a class when it is divided by 4, so we'll have four possibility, 4k, 4k plus 1, 4k plus 2 and 4k plus 3. Now these two are even, so I'm going to drop up. Only these 4k plus 1 and 4k plus 3, these are the cases when they will become odd. So whenever a is odd, I have considered a 4k plus 1 and 4k plus 3, k belong to integer. Now whenever a is 4k plus 1, so in this case a square, this will become 4k plus 1 whole square, and if I open this will become 16k square plus 8k plus 1. And we notice that if I take from these two, we can take 8 common, so we'll have 2k square plus k plus 1, and the remainder is 1. This is appearing as a multiple of 8. So this is obviously congruent to 1 mod 8. So we got the result as we desired. A square is congruent to 1 mod 8. Similarly, when a is 4k plus 3, I am going to open a square, which is 4k plus 3 square, and this will become 16k square plus 24k plus 9, and so we take 8 common, so we'll have 2k square plus 3k plus 1, and this 9 also we can write it as 8 plus 1, that 8 is here and plus 1 remaining is here. So this is congruent to 1 mod 8, and that proves our second case also. That means whenever a is odd, we have taken both the possibility. A square is always congruent to 1 mod 8. Now for B part, we want to show that a cube is congruent to 0, 1 or 6 mod 7. So now since we are doing with respect to mod 7, so we can simply use division lemma, and here we are dividing this any integer a with 7. So the remainder possibility is 0 to 6, and then we take cube. So for all possibilities of a, we can simply take different cases for a, 7k cube, 7k plus 1 cube, and so on, 7k plus 6 cube. We find here that the least remainder is 0, 1, 6. So these are the 3 possibility, and hence it proves the result. Similarly, in C part, we want to prove for any a to the power 4 is congruent to 0 or 1 mod 5. Again, using division algorithm, we can have a can take 5k, 5k plus 1, 5k plus 2, 5k plus 3 and 5k plus 4. And then we take fourth power of this, we see that this is either 0 or always 1. And that proves our C part. We could reduce this step rather than checking all. We could simply call it as 7k plus r times whole cube. And then we can open 7k cube plus r cube plus 7k square into r 3 times. And then 3 times 7k into r square. Now you can see that this term also contains 7k, this term also contains 7k. So all of these are congruent to 0 mod 7. The only term which is remaining is r cube mod 7. And now for different values of r, so for example r can take 0 to 6. So here you can take different values for r, and you can conclude directly from this expression also that this will reduce our expression 0, 1, 6. Similarly, in this case also you can reduce your calculation by directly opening 5k plus r raised to power 4, and then conclude your result depending upon what is the value for r. In D part, we'll prove if a is not divisible by 2 or 3, then a square is congruent to 1 mod 24. Now as we say a is not divisible by 2, so we can simply write a is not congruent to mod 2 and a is not congruent to 0 mod 3, because also it is not divisible by 3. Which means a cannot be even. If it is not divisible by 2, this is not even. And this means a cannot be 3 or multiple of 3, because if it is a multiple of 3, it will be divisible by 3. So, or we just have 2 does not divide a and 3 does not divide a. So now I want to show that square is congruent to 1 mod 24. So let's say if a is divisible by 24, what the division lemma says. So using the division lemma, a is 24 into quotient plus remainder, and remainder will take the possibility between 0 to 23, or I can say remainder takes less than 24. So here as a cannot be even, so we'll exclude the even possibility, and here I'll only take the possibility when r can be odd. So that is 1, 5, 7, 11, 13, 17 and 19. And so a square, because we want to conclude for square, a square is congruent to 24 times. So squaring this quantity, let's say from equation number 1, I'm squaring on both sides. 24q square plus 24q into 2 and then into r. This is the formula 2ab into r square. Now both terms contain 24, so this means this is simply congruent to plus r square mod 24. So our result depends upon only r square. Now taking different values for r which I have listed here, we'll conclude about this. So let's take one case. When r is equal to 1, a square is congruent to r square and r value is 1. So this is congruent to 1 more 24. If I take one more case, let's say r is equal to 5. In this case, we'll have a square. This is congruent to r square and r value is 5 square. 5, this is 25. 25 is congruent to 1 more 24. And we continue doing like this. So for all values, we will verify. When r is 19, a square, this is congruent to 19 square. 19 square, this is 361. 361 is 15 into 24 plus 1. So which is congruent to 1 more 24. So we will conclude that a square is congruent to 1 more 24. That proves our result. In ninth problem, we want to prove if p is prime such that p lies between n and 2n, then 2n choose n is congruent to 0 mod p. And for this problem, let's see 2n choose n. So this I am going to apply the formula NCR, that is equal to n factorial upon r factorial into n minus r factorial. So this will become 2n factorial upon n factorial into n factorial. When I open this one, this becomes 2n into 2n minus 1 up till n plus 1 into n factorial divided by n factorial into n factorial. One of the n factorial get cancelled. So we have 2n into 2n minus 1 up till n plus 1. And this n factorial I am going to cross multiply. So this is n factorial into 2n choose n. So we got, let's call this as equation number 1. Now I'm going to use one of the conjecture, and Burton conjecture says that between n and 2n there exists a prime. So n less than p less than 2n, or we can simply say there exists a p prime such that this prime must lie between n and twice of that integer. So p must be one of the factor, the terms which are appearing on the right of 1, that is 2n into 2n minus 1 up till n plus 1, or I can write in the reverse order. Say I write n plus 1 here, and then we have n plus 2 here, and then we have 2n minus 1 into 2n. Now notice that this last term is 2n and this term is strictly greater than n. So we can say that this term is strictly greater than n. Notice that n plus 1 is strictly greater than n. This means, this shows that using the Burton conjecture, there must be a prime p which lies between n and 2n, and that means p must be one of the factor among this, and this whole terms are coming as a product. So p must be dividing the whole product. So we can simply say p divide this whole product 2n up till n plus 1, or I can simply say 2n up till n plus 1 is p into some k dash, where k dash belongs to integer. And we also notice that as p is strictly greater than n, so obviously GCD of n factorial and p, this is 1, because in n factorial we will have all the integers which are either which are less than or equal to n, but p is greater than n, so obviously p cannot be common with the smaller integers. So we'll now apply the Euclidean lemma on equation number 1. So on 1, and the first equation gives us n factorial, this is into 2n n, this is equal to this expression which is the product of these factors 2n, 2n minus 1 up till n plus 1, which we have written p into k dash. So this will become p into k dash. So from here, and using the Euclid's lemma, what we can say, we can simply say p divide n factorial into 2n choose n, and we have shown that the GCD of n factorial and p is 1. So here I am going to apply actually the Euclidean lemma. This will imply p divide 2n choose n. So when p divide 2n choose n, because p cannot divide this n factorial as the GCD with p is 1, so this will imply 2n choose n, this is congruent to 0 mod p. and that proves our result. We wanted to show that 2n choose n is congruent to 0 mod p. In question number 10, we have been given that the set A1, A2 up till An is a complete system of residue modulo n and the GCD of A and n is equal to 1. Then we want to prove that this set A, A1, A, A2 up till A, An is also a complete system of residue mod n. And to show this, we will simply show that any two integers in this set, they are incongruent to each other. So this is what we want to show. Aij should not be congruent to Aaj mod n for 1 less than I is strictly less than j less than or equal to n. We may also take I is greater than j. So to prove this, we'll take on contrary. Let's say on contrary, they are congruent to each other. Aai is congruent to Aaj mod n. Now we can apply cancellation law on both sides, as we notice that the GCD of A and n is equal to 1. This is already given to us, this condition. So cancelling A on both sides, we get Aaj is congruent like this. Ai is congruent to Aj mod n. But we have already given that this set is complete system of residue, which means in this set Aai cannot be congruent to Aaj for I different than j. Only when I and j are same, then it is allowed. But here in this condition, I and j are not same. So this contradicts our given assumption, which contradicts given assumption, and hence our result that the set this is also incongruent and it forms a complete system of residue. Now to form the complete system of residue, there must be n elements, and we can see from the subscript there are total n elements in this set as well. Also in my previous given set, we have n number of elements. So this is complete system of residue mod n.